I will first introduce 4 steps in parallelizing a sequential program, explain 3 issues that can reduce the performance, and reflect on how Akka is related to these problems, and then talk about multi-core architectures. And we will actually start with the very first computer, and then look forward in a quite fast pace on the development of computer architecture. The purpose of seeing the development of computer architecture is twofold. Firstly, to see some interesting persons who have changed the industry, and then to see that most fancy ideas about how to design a parallel, very fast computer, these ideas have been around for decades. Some of them lead to economic disaster for the company, and others for mass market acceptance. And you should be very well aware of what is at stake. I mean, what makes a successful parallel machine. Okay, so that's the main part of this course, of this lecture. So, first, let's assume that memories and cache memories are slow. There is a small chance that you have not taken a course about cache memories. I mean, not only cache memories, but let me explain it extremely briefly here. A cache memory is like a small memory with contents that is a copy of the data in the main memory. Look at it as your desk compared to your bookshelf. You put the most commonly used books on your desk, and when it's not available there, you may go to the bookshelf and get it. Okay, so that's a very simple description. I will come to a much more detailed description of cache memories, and in particular about cache memories for multiprocessors in a later part of the course. But there are 3 main issues, but if we ignore that memories are slow and caches are useful, there are only 2 left, and they are program correctness and load imbalance. Obviously, we must have a correct program that can be achieved with different amounts of efforts depending on which language we use. But it's not only sufficient to have a correct program, because then we would not use a parallel program, since it's easiest to get a sequential program correct to begin with. Another aspect which is really important to get good performance is load balance. If we don't have load balance, then some processors will work more than the others, and since the execution time is determined when the last work item is completed, it is very important that all parts of the machine work approximately as much as the others. Otherwise we have to wait. If we compare with human beings, we always have to wait for the one who is lost. Well, that's quite obvious. And we want to see that not one of the processors is very much behind the others. Okay. Unfortunately, memories can be hundreds of times slower than a simple operation in a CPU, such as adding 2 integer numbers. Okay, and then for parallel computers, when we say that the two threads or actors communicate, that usually results in cache misses, because some data is sent to another actor. If that actor, I mean the receiving actor, happens to be executed on the same CPU, then there will be no cache miss. But if it's on a different CPU and a different cache, the data obviously must be copied to the destination. And another issue is that, okay, that's for actors. And for normal threads, when a thread reads data from memory, it usually means that it has been written by another thread that has the copy left in its cache. So the data must be copied either directly from the writing, from the cache that writes to the cache that needs it, but usually that goes through the main memory. And this communication, I mean reading and writing the data to main memory, this is what takes most of the time. Usually, not always, of course. If each thread can work a lot with it, I mean do lots of mathematical operations without being bothered about cache misses, then that's very easy to parallelize. For pre-flow push, we have a very interesting situation, because each work item of pushing data to some neighbors or increasing the height of a node, it's really small. So this makes it an interesting problem to parallelize. Okay, another thing is that cache memories in multiprocessors can, if we write buggy software, then they can introduce obscure bugs. And all multiprocessors have some form of cache memories, which means optimizing performance usually means exploiting them better. And that's the third issue. Okay, let's now look back at Akka and see how it deals with these three problems. So, correctness with Akka, it's not that difficult. If we can make a good design without races between messages, I mean from different actors reaching a certain actor, then it's usually quite easy to get it correct. It's not trivial, as you probably noticed, but it's possible to be convinced that this actually works without any issue. Okay, and that's why Scala, actors, and Akka are used to a very large extent. Not the best performance, but it's more reliable and easier to get working. Okay, load balancing. Well, what we do is to have numerous actors, and we don't have to think about load balancing, since the actor system will give one actor to a thread, and that thread will perform what the actor needs to do when it has received the message. So that is done automatically. And that's really nice, to not have to think about load balancing. Okay, but there is, I mean, as soon as we have an automatic system, there is a risk that it does not perform perfectly. And if the system does not have the proper insights as a human being may have. Okay, so there is a risk with Akka that data is copied between different cache memories. If the sending and receiving actors happen to be executed on different threads and CPUs and cache memories. Okay, and also by itself, sending and receiving messages usually take more time than just writing and reading a variable in memory. But just writing and reading variables in memory will give us other problems to avoid data races between the different threads. Okay, so let's look what is, I mean, this is for a conventional language such as Java or C or C++. What is actually shared between different threads? Global variables, that means in C and C++, variables that are declared outside any function or class. And for Java, that means static attributes in a class. Okay, or data allocated with new in Java and C++, or malloc or calloc in C. This data is automatically shared. Data allocated on the stack when a new function is called, that's usually private. I mean, it is private, but for C and C++, we can take the address of such a variable and give that address to another thread. I mean, they live all in the same address space. I mean, the variables are in the same address space, so as soon as one thread has the address of a variable, it can modify it. Okay. So for Java, that's not possible, since we cannot take the address of a local variable on the stack. So what is the most convenient way to get high performance of a program, of a sequential program? It certainly is to use a parallelizing compiler. And if we can get good enough performance, we can be done within 10 seconds or less, typically less. Well, it depends on the size of the program, of course. Okay, we will come back to one lecture about the parallelizing compilers near the end of the course. The second most convenient way to parallelize a program is to do it incrementally. That means parallelizing one loop at a time. Okay, for preflow push, there are not that many loops, so it's not much applicable in that algorithm. But say for a numerical computation, there may be numerous loops, and by measuring which one takes most of the time, we can start looking at how that loop can be parallelized. So that means having the most of the code sequential, but parallelizing one loop at a time. That's completely different from switching from sequential program to actor model. With actors, we have to parallelize everything at once, meaning rewriting the program to be parallel. Incremental parallelization is supported by something called OpenMP, which is available for C, C++, and Fortran. And there are other ways to do incremental parallelization as well for other languages. And what we basically say is that this loop can be run in parallel, and the compiler trusts us. So it's up to the programmer to make sure, I mean, to guarantee that this loop actually can be parallelized without corrupting the data. Okay, and if neither a parallelizing compiler nor OpenMP or equivalent is applicable, then we should parallelize by hand. And then we move to this and address one topic at a time.